Hello, now it's Friday morning, and I'm going to give part C a little work. This transformation formula should come in handy to the cusp at -1/2, and of course the generator of gamma naught of 4. But let's start with the expansion at infinity. That's easy. It's dominated by q, 1 times q, like minuscule f is. So let's try at naught. And it's the definition. I wonder if we can use anything in problem 9 for this. No, nothing in problem 8. And we must use the transformation formula. So z squared we already have here, so we'll delete that from the outside. And then we need the transformation formula for E. So 1 divided by z was E2 of z plus 12 divided by 2 pi I z minus 3 times. And now here it's minus 2 z's, so that means it's z squared halves. Can't have that in my head today, so I'll just do it over here. And then we'll insert z halves into the formula for z. And plus 2, and that sets 4, that's 2/16. Plus, and then 2 times 12 times 4, that's 48 z, and then the larger parenthesis, or the outer parenthesis. And now let's see what we have here. We have (12) minus 3/4 of 24. That's like 18. Plus 1/8 of 48. That's 6. That gives naught. We need to check that the constant vanishes. So the constant, it's from E2, we get unity, then -1/2. No, that's silly. We need to compute the constant. And then plus 1/8. That's 8 minus 4 plus 1/8. It's 5/8. So it's 5/8 plus something. And next we need to do the same at, of course, starting with now what about the 24th? I didn't get that. So we have to divide by minus 24. My God. I'm never thorough enough. And then the first term here, it's 24 times Q4. So it's minus 1/8 Q4, etc. I don't know what we get with Q4 squared, never mind. So it has the right form, and the value at naught, I get minus 5 divided by 192. And doing the stuff here at at 1/2, that is setting a equal to 2, we might have room enough for it. And 20 minus, oh my God. I'm sure I won't have room enough for it. It's minus 1 divided by 24. And then we start. First, E2 of Z. This is squared. That was E2 of Z. Next, we have minus 3. E2 of 2Z. That means we take this guy and insert 2Z in the expression. As you can see, I feel I'm doing something wrong here, but we'll just go along. And then plus 2. And then it's 4Z. This feels wrong, very wrong. it means I'll make a break and then do it on paper and tell you the result. I'm back. It's now Sunday, so I've really had a hard time figuring out what went wrong here. Let's start with this calculation, which of course should give the same result as in problem, I guess it was in, it's in part A, 10A. And we got this, which is not quite what we should have. So where's the mistake? First, I thought if this was minus, then we would get 3/8, and I think that would do it. But that was the right sign I had. It did give plus. But then next 3/4 of 25, that's 18. Oh, that's what I got. Now where am I? It was down here at the cost. It was 5/8 what I made here. Oh, that came from the constant term of E2, which was unity. That gives 8 minus 3/4. That's 6/8. That's 2 plus 1, that's 3/8. Oh, that gives 3 here. So that's 1/64. And a minus as well, and that's minus 2 to the 6, exactly as we got in problem 10A. Now this was really terrible, because what we have to compute is E of 2 times all of this, not this of 2z. So that was terrible. I did right in feeling it was wrong, but I must admit that I only did it because the result seemed very off. So we must start doing this anew. So let's try E2 of 2 times let's do them individually. And then it was z divided by az plus 1. And a may be 2 or 4. So we'll just note that we only need those 2 cases. And then we use the transformation formula. It's the lower one. We flip this, and it's a halves minus 1 divided by 2z minus 12 divided by 2 pi I 2z times az plus 1 and this guy will be an integer, and we use the formula again. Let's just flip this fraction or this parenthesis. 24z minus 12az, 12 times 2 minus a minus 12. Oops! There's a z down there. So I'll just have a look at that. All right, I've found the mistake. We need a parenthesis around these two guys because this was outside. We do get this, and then 4z, that gives 2z down here, and then we have az plus 1 squared minus az plus 1. And then finally, those two z's cancel. That was 2a. I will now stop recording and do the same for 4a on a sheet of paper, and then write the result. I couldn't quite do what I said I would, but I could do it for the transformation with the generator of, or the last generator of our group. And first, let's do minus 24, so it's only E2, etc. E2 we have from the problem itself. So that comes here. So it's E2 of z, and up here in the numerator it's 12 times 4, that's 48. And then minus 3 times the result of E2, which we have up here. Here a is 4, so that gives a factor 2, that's 24. And finally 2 times E2 of 4z, and then plus 12 times 2, that's like 24. And we collect these first. Let's do it in blue. That's minus 24 f of z. And then the rest, it's 48 plus 48. It's 48 plus 48. That's 96 minus 92. Now that doesn't make any sense. 12 to 6, 72. That had to vanish. I'll just find that mistake after recording. Now the last term we need E2 fourth set of E2 of fourth set when we transform it with this matrix. Now forgetting this, just operating E2 on 4 set, 2 set plus 1. When we do what I've been doing up to now, we use this guy. And then minus the reciprocal, that gives minus 1/2. And minus 1 divided by 4 set. And then plus 12 something divided by 2 pi I, etc. But this is the guilty party. The rest ought to vanish when we put it all together. But this minus 1/2 I don't know what to do with that. We have a formula in one of the exercises, by the way. Where we only sum over the odd ends. And then that's q to nth. But that means that we have here to use, instead of q, e to minus 2pi divided by 4z. Basically, we need to find the transformation formula for... we have to go back to chapter 2 and have a sum. Well, forget it, because it's the difference here is the formula the modular form we are working on. So that means that solving this problem is equivalent to solving to proving that capital F itself is a modular form. So we'll leave that for the time being. So that's not the right way to do it. There was another thing I was thinking about, and that's we proved in, that wasn't problem 2, that this guy is periodic. And actually, later on, it is periodic with period 1. Unity. And that means that the Fourier series converges, and that's just q with integer powers. So we know as much as that, but we still need to prove that we only have a finite number of negative ones, and in our case that they are all greater than or equal to naught. All in all, I need to be able to do something with this expression before I can say that I have solved part C. But we have made progress and actually proven now, that is, when I correct this mistake I've made, that it transforms correctly under this matrix. And of course translation 1 and S. Good morning. It's now Tuesday, December the 5th. Yesterday we stopped while I didn't know how to handle this, and then in the late afternoon I got an idea. So I'll just show it to you. It was to subtract 1 in here. If we subtract 1, then we end up with 2z minus 1 divided by 2z plus 1. And that might be tractable, though that is a little complicated. But then if we subtract 2, we get minus 2 divided by 4z plus 1. And this is eminently tractable. So we need to apply this formula, E of z, or E of 1 divided by z, minus 1 divided by z. We need to apply it with z. Then we are done. Now going back to the error I made in this calculation. Is there a method to these numerators? I looked like it was 48, 24, 12, meaning there was a mistake here. And then this morning I realized, well, we can use the same idea here. So let's try that. Instead of doing my complicated computation. So we just subtract 1. And then we apply the formula. And we have it here. It's 1 divided by z, z squared E of z, plus 12z divided by 2 pi I. And this, of course, is E2 of 4z plus 12 this means it should be 12 in the numerator here. And that means we get 48 Is this a minus? It should be a plus. Let's assume it's a plus. 48 plus 12, that's 2 times 12. That's 72, as is 3 times 24. The others are plus, so this must be as well. I'll not be looking for that error. So the last thing we need to have finished C, that's compute the entire expansion of was f of z, I think. And find its Q expansion. Oh, I didn't finish this, by the way. Well, let's do that when we make this calculation. So again, we take minus 24 times it, so it's only e2 of z minus 3 e2 of 2z plus 2 times e2 of 4z. And I've got them all somewhere. I'll just see what I've got the different places. That was e of z. Then e of 2z. We did calculate it here. And finally plus 2 times. We need, of course, to multiply by 2z plus 1 to minus second, so they cancel. So it's 1/4 of z e2 of z plus, my God. This may look terrifying, but there is an easy way to handle it. I'll show you in a minute. And that was part of the idea I got yesterday. So it was a combination of translating here, which saves us a step sometimes, and then having e2 of z. But first we need to see that these actually cancel out. So 2 times 1/2, that gives unity, plus 2, that gives 3. And that's what we get here. So these annoying terms cancel as they must. It was very nice. So we are left with e2 of z minus 3 e2 of 2z. Or is that z? Where did I do that? It's actually e2 of 2z. Yeah. Plus 1/2 e2 of z plus 1/2. It's actually in the problem 8b. That this equals Ez e2 of z plus the sum from n equals 1 to infinity, only n odd. So we only have positive powers of q in this expansion. And therefore we just need to compute the constant term. E2, that's unity, minus 3 plus 1/2. And this, of course, starts with q to the first, giving minus 6, minus 2, that's minus 4, that's minus 3/2. And then we need to divide by minus 24. So the leading, or the value of f at minus 1/2 equals 3 divided by 224. That's 1/8, that 1/16. That's 2 to minus 4th. I really do think that was the same we got at the start for the other function I called minuscule f. All right. Now we have the two modular functions of the group gamma naught of 4, and we should prove that they are identical, but I think that's just application of theory or a proposition in the book. Yeah, it's proposition 18. So we'll consider the function. Now we use h of s, h of z equals minuscule f divided by g of, it was called capital F of z. It's obviously a modular function of weight 0, a modular form of weight naught. And it's a form because, we can make the power series expansion everywhere. So it just works out nice. And then by proposition 18, it's a constant. And since they have the, it's actually unity, because at infinity they both go as q. And of course, then we can conclude that they have the same value at the other cusps, which we have now computed explicitly. Therefore, they are equal. And I think we have had that formula already as the expansion of this function. And I did check this one numerically. That's what I'll show you today.